So now today's class is all about the test of independence. So what do we mean about test of independence? So to understand this concept, I will try to take one example. For example, let's say in our SCT college, let's say we have a population of, let's say, around 5,000 people. Okay, we have 5,000 people in our SAT campus, including faculty and student. I'm roughly taking some 5,000 people. So this represent our population, let's say, the population. So this 5,000 people in our SAT campus will be of different age group. Okay. Now I want to do a study, or I want to have a study that the age group. Okay, if I set some kind of age group, let's say if I say 20 to 30 years of age group and 30 to 40 or 40 to 50 of age group in roughly. So, and the brand of phone, let's say some brand of phone, let's say Realme, and then let's say another brand at the Samsung, and another company put, let me say Apple, okay, iPhone. So I want to check that whether is there any relationship between the age group and the brand of the phone. Brand of the phone. What I mean by that is the particular age group. Does there any relationship that between 20 to 30 year of age, there some particular brand of phone they will use, or between 30 to 40 age group they may use some other brand of phone, or 40 to 50 year of age they may use some other brand of phone. So I just want to do a test, or to check the relationship between. So is there any relationship? Is there any relationship between the two factor here, which is age group and, let's say, brand of phone, the brand of phone. So I want to check whether is there any relationship or not. So to check this relationship, what I will do, that I will, from this SCT campus of 5,000 people, I will take some sample. Let's say I have taken around 400 people, and I have asked them randomly that what kind of phone they use. So, for example, let's say total number is 400 people of sample I have taken, and I have found out that 20 to 30 group, let's say 40 people they use Realme, and let's say 40 people they use Samsung, and let's say 60 people they use Apple. Some rough figure I'm taking. Similarly, some other 30 to 40 category, let's say 20, maybe 40, and then 20, and so on. So if I put all together, the total number will be 400. If I sum all this, it should be 400. So 400 people have selected randomly from the 5,000 people in SCT campus. So I have collected some data. So I cannot ask all 5,000 people. So I have taken some sample, as we know that we do the sampling. And then we have categorized this in a tabular form. So when you categorize this in a tabular form, this table which you have written like this in the age group and the brand of the phone, this table we call that as contingency. We call that as contingency table. Okay, so we will prepare a contingency table like this, and then based on this contingency table, I will try to find out whether is there any relationship between the age group and the kind of phone they use. So basically what I have to do in this case now, your null hypothesis which you formulate initially is that your two attribute or the two variable, I can put in this way, the two variable. In this case, the two variable is age group and the brand of phone are independent. This will be our standard null hypothesis. So when I say two variables are independent, in this case, what I'm telling that the age group and the brand phone, two variables are independent. It means there is no connection between the age group and the brand phone. This is what I am assuming as initial hypothesis. All right. Then your alternative hypothesis becomes that your two variables are dependent. Your two variables are dependent. So these are the two hypotheses we will formulate initially. Your null hypothesis will be standard that whenever you are finding the relationship between any two variate, in this case we have age group and the brand of phone. So initially you are independent. In this case, our age group and brand of the phone are independent. So I'm assuming that initially there is no connection at all. So to do this hypothesis testing, we will follow some steps. Let us see one by one what we will do in this case. All right. So as I've taken that example, that this is the relationship between the age of the person and the brand of the phone they use. So to understand this relationship, let us say we have asked randomly around 365 people. I have changed the number. 365 people we have asked randomly of different age group, and we have found that this is the data. This 365 people which we have asked randomly, which we have taken a sample out of population. Population can be bigger and bigger. We don't bother about the population. The sample which we have taken, and we have collected some data. We have found that 20 to 30 year of age group use 20 out in that 20 people use Realme brand phone, 80 has used Samsung, and 40 will use Apple. Then 30 to 40 year of age group, 15 people use Realme, 60 will use Samsung, and 65 will use Apple, and so on. Now in this case, the most important part is your row total, which will be a total of 20 plus 80 plus 40. So 80 plus 20 is 100, 100 plus 40 is 140. So you add all the rows and you have to add all the columns as well. So first you add the column like this, column wise you have to add, okay, and also you have to add the row wise. So this much data you have to collect. So now remember that this table which we have now, and which the table which we have formulated, we call that table as contingency table, right? And these values 20, 80, 40, 15, 60, 65, 5, 50, and 30, they all are your observed frequencies. I repeat once again, the data which you have collected from the sample, those frequencies are your observed frequency. With these frequencies you have observed, which people have told you that different age group use what kind of brand phone. So these are your observed frequencies. All right. So now we have come across that the table which we formulated is called contingency table, and these data which we have is called a observed frequency, which is represented with Fi. All right. And now we have to test the hypothesis for the relationship between the age of the person and the brand of the phone they use. So it means I'm checking whether the age of the person and the brand of the phone are independent to each other or dependent to each other. This is what we have to test the hypothesis. Now, to test this hypothesis, let us formulate our H0 and H1. So H0 will be age of person and brand of the phone are independent. Always you have to take your null hypothesis as independent. It means your null hypothesis, you are telling that age of the person and brand of the phone has no connection, okay, at all. But your alternative hypothesis will be the reverse case of that, in which the age of the person and brand of the phone are not independent, or we can say dependent. So hypothesis formulation is simple. Now to test this hypothesis, we again use the chi-square test. So we quickly recall our chi-square formula. We already know that chi-square is nothing but your observed frequency minus expected frequency. You have to square that and divide by your expected frequency, and you have to take the summation of all. This is the formula we have seen previously. All right. Now to uh, find the chi-square value, now observed frequencies are already we have from the previous table. If you just go back, these are the observed frequency which we have already collected. So this 20, 80, 40 and all those data are observed frequencies. Now observed frequency we have. Now major thing is now what? We have to calculate the expected frequencies. This frequency we have to calculate. So kindly pay attention how to find the expected frequencies. The calculation of expected frequencies are very different concept in this case. So I will go very slowly, because once you understand the expected frequency, how to calculate, then done. The problem itself is completely done. All right. So now this is your chi-square formula. This is the test which we use to test the hypothesis. So note that Fi we already know from the data collected. Now we have to calculate the expected frequencies. So to calculate the expected frequency, use this formula. I have written very simple formula. The row total multiply with the column total whole divided by the total number of sample size taken. I repeat, row total, it's a row total, okay, multiply with the column total divided by the total number of sample size taken. Remember this, okay. So now let us calculate the expected frequencies. Fine. Now this is the data which we have collected. Same data I have taken as it is. So now to show you, I will show you how to calculate the expected frequency for this one and fh. I marked that in green color. The pink color is the column total. So this will be your column total 1, column total 2, and column total 3. And the yellow color is represented as row total 1, row total 2, and row total 3. Now pay attention. If I want to find the expected frequency for, let's say, age group 20 to 30, now I'm finding the expected frequency. Let me put E1. And the expected frequency is that I have to find the expected frequency for age group 20 to 30 and the brand of the phone Realme. Okay, so I have marked that as E1. So how you will calculate that? Our formula is simple. Row total multiply with column total divided by total number of sample we have taken. So now you can see we are talking about 20 to 30 age group in Realme. So we are talking about F1. Okay, so you have to take the column total. So first row total you take. So what is the row total? I'm sorry. One second. Okay, yeah. So what is the row total? Row total is 140. So that will be 140 multiply with the corresponding column total, which is 40, and whole divided by the total number of sample we have taken, which is 365. We have asked 365 people. When you do that, you will get your even value. So roughly you can calculate. I don't know what is the value. Now, similarly, if you want to find the expected frequency for, let's say, this particular cell. So this particular cell represents the age group 20 to 30 and the brand phone Apple. So I will write this as E3 because it is F3 here. These are all your observed frequency, Fi, So Fi means F1, F2, F3, F4, F5, and so on. So E3 represent your age group 20 to 30, and the brand phone I'm talking here is Apple, let's say. So the expected frequency will be your row total, which is again 140 in this case, and your column total will be 135, and whole divided by the total number, which is 365. So when you calculate these values, so quickly we'll just calculate that. First value is 140 into 40 divided by 365. It is coming around 15.34. All right, and this value is coming around 140 into 135 divided by 365. This is coming around 51.78. Okay, so like that, for every cell we have to calculate the expected frequencies. All right, so now you understood how to find the expected frequencies. So again, I have repeated, this is your observed frequencies given, and now we are calculating the expected frequency. So for example, let's say 20 to 30, and brand phone Realme, which I'm talking about, green color shaded, F120. So as I've told you, the row total is 40 into 140 divided by 365. So value is 15.342, which I've written here. Now another example I've taken as this one. So we will calculate the expected frequency for the age group 40 to 50. I've taken age group 40 to 50, and the brand phone Samsung. So we are talking about F8. So for F8, your row total is 85 into column total is 190 by 365. It is coming around 44.247. So like that, we will calculate all expected frequencies. So this is the expected frequencies I have calculated. All right. Now, once you have calculated your all expected frequencies, now you can use your chi-square formula, which is summation of observed frequency minus expected frequency whole square divided by EI. So what I have done in this case is, this value I have calculated in tabular form, and then I will add this value at the end. Okay, so you know that your observed frequency, let's say for this particular cell, if you want to find the value of chi-square, then this value will become 20, because your observed frequency is 20 minus 15.34 divided by EI, which is again 15.34. When you calculate that, that will be your this value, this formula value for the first cell. So to simplify the calculation, I have just calculated this particular value in the tabular form. All right, whereas this value is nothing but this is your F1 minus E1 whole square divided by E1. So for this will be your F2 minus E2 divided by E2, and this will be whole square. Like that, I have calculated and written all the values now. So you can see these values I have already calculated. So for chi-square, I had to just do the summation now. So we will add all this value, 1.42 plus 0.70 plus 2.68 plus 0.01 and so on up to here. So when we add, we will get the chi-square value. So we have added all the values, and we will get the value as 13.28. So we are testing this hypothesis at 5% level of significance. Now in this case, one more important concept is, what is your degree of freedom? Your degree of freedom in chi-square in general, n-1 we will take. If we just go back to previous classes and check, for all the problem in chi-square, we have taken degree of freedom as n-1. But in this case, you have two variable included, like we are checking the independence of two variates. So the degree of freedom will become the number of rows -1 and number of column -1. Quickly let us check how many rows and columns we have. We have 1, 2, 3 and 1, 2, 3. So we have 3 columns and 3 rows. So your degree of freedom will become how much? For this example, 3 minus 1 into 3 minus 1. So which is 2 into 2, 4 is the degree of freedom. So now therefore you have to just find the critical value of 5% level of significance at 4 degree of freedom. So you have to go back to your chi-square table. So we can just quickly go back to our chi-square value. Just where we had the chi-square test values previously. Yeah, here. So if we just kindly see this chi-square value, we want to check the chi-square of 5% level of significance and degree of freedom is 4. So what is the value? Here is the 5% and degree of freedom is 4. So what is the value? It is 9.49. So table will not change for test of independence. So this is the critical value. We have got it, which is 9.49. All right. So let's go back to that problem. This problem, yeah. Set of problem. Okay. So we had degree of freedom. So see, we have the value 9.49. So now we have to just compare. So you can see in this case, your chi-square value, which is 13.28, is greater than 9.49. It means your chi-square value is greater than the chi-square critical value. So when you plot the chi-square distribution, it will be something like this. So this will be your critical value. This is your chi-square critical value, which is in our case, this is 9.49. So this is 9.49. So if the chi-square value lies in this region, then we have to reject the hypothesis. And if it lies in this region, we have to accept 13.28 is more than 9.49. So it is coming here. The chi-square value is greater than 9.49. So we have to reject the hypothesis. So we have to reject our null hypothesis and you have to accept the alternative hypothesis. So if we have to reject the hypothesis, then what it concludes? Infer means conclusion. So hence we can conclude that the two variable, which is age group and the brand of the phone, are not independent, which means that the person age does influence the brand of phone. It means if the person is 20 to 30, then they have some popular brand phone for this particular age group. And if the age group is 30 to 40, they have some more popularity. So it means the person age and the brand of the phone are dependent to each other. So this is what the test of independence tells you about. So this is the degree of freedom value I have given, which was 9.49 and 4 degree of freedom. And this is the chi-square curve. So our chi-square critical value was 9.49 and the chi-square value was 13.28, which was at the rejection region. That is why we have rejected the hypothesis. Only in the green region we have to accept. Rest all the region we have to neglect. Okay, it's a one-tailed test because chi-square value is starting from 0. Because if you see, if your observed frequency and your expected frequency become same, then your chi-square becomes exactly 0. So it will be start from here. So we do not have any other tail apart from the right side. So basically the chi-square test is deal about the right tail test. These questions may ask in MCQs that chi-square is one tail or two tail. Chi-square cannot be two tail, it will be always one tail. Okay. Anyway, so let us look at the summary. So the test of independence determines whether two factor or the variables are independent or not. So test of independence involves the contingency table, which we have seen. This contingency table will be having observed frequencies, okay, from which we can calculate the expected frequencies. So the test statistic to test the independence is the chi-square, which is this formula, and the degree of freedom is root number of rows minus 1 into column minus 1. And if your chi-square value is greater than chi-square critical, you have to reject the null hypothesis, where H naught is our standard statement of hypothesis, where you have to always take that two variables are independent. So this is all the summary. Let us quickly look into another problem. What's the time? It's 12:06. All right. Okay. Let's say what is this problem tells about. Okay, in a survey of 200 girls, of which 75 were intelligent, okay, 40 had skilled fathers. Okay, just try to understand the statement. In a survey of 200 girls, they have done the survey of 200 girls, so 200 is the sample size, and they found that 75 girls were intelligent, and those 75 girls who are intelligent, out of that 75, 40 had skilled father, means their fathers are also intelligent, they're trying to say. While 85 of unintelligent girls, means 85 who are not intelligent girls, had unskilled father. So they have some data which they have got from the survey. So do this data support the hypothesis that the skilled father have intelligent girls? Now in this case we have two variables. One is skilled father and the intelligent girl. So we have two variables included here. So they want to test the hypothesis that if the father is skilled, is also implies that the girl will be intelligent. This is what they want to check, the independency in between that, whether they have some independency or not. They want to check that particular part. So I hope question is clear. So to answer this question, first let us formulate our null hypothesis. So null hypothesis is very simple. We all, as I told you earlier, that two attributes are independent. We always take that as null hypothesis. So in this case, the two attributes is nothing but your skilled father and intelligent girl. So if you say two attributes are independent, means I am assuming that the skill of the father does not have any effect on intelligence of girls. I'm taking an initial assumption that they both are independent. If you have a skilled father, it does not mean that the girl will be intelligent. This is my initial assumption. Okay, and or H1 will be its reverse, that two attributes are dependent. It is understood now. So now what we have to do first, this given data we have to put in a contingency table. So let us first write the contingency table in this case. So what does the contingency table look like? So as a given data, let us first put the data as what we have. In a survey of 200 girls, so n value will be 200. All right. 75 were intelligent. Okay. So intelligent girl, total number is 75, they have already given. Okay. Now 40 had skilled father. So skilled father and intelligent is 40. Okay. Intelligent and skilled father number is 40. So just put the number 40. So if 75 is there, 40 is there, 75 minus 40 will be 35. So this will be 75 minus 40. This value will be 35. Next, while 85 of unintelligent girl had unskilled father. So unskilled father and unintelligent girl is 85. Okay. So if you have intelligent girl as 75, then 200 minus 75 is 125. Just put here the number, and the 125 minus 85 will be 40. I just put the blank column. Now once you have filled all the data, just take the row addition, which is 40 plus 40, 80. 35 plus 85 is 120. 7, and this addition also you have to take, which is 75 and 125. So this contingency table you have to put based on this data. So these are your observed frequencies. Okay. Now you can see that all the observed frequencies values I have written here. So 40, I have written 40. This is also 40, so I have written 40 here, which is 35, 35, and 85, 85. So I have written the observed frequencies. We can calculate our expected frequency with the same formula. What is the formula for expected frequency? Row total into column total by n. So if you want to find this particular value, it means where the observed frequency is 40, this value, so the corresponding row total is 80 multiplied with 75 divided by 200, you will get 30. So check this. So like that I have calculated all the expected frequencies. Okay. Where the 30, this value has, as I've told you, this is 80 into 75 by 200. 80 into 75 by 200. So if you want to check the value for 45, this value how you will calculate? So 35, where is 35? First identify the 35 in the contingency table. Here is the 35. The row total is 120 into the column total is 75 whole divided by 200. So when you calculate this, you will get 45. So like that, expected frequencies I have put in the table. Now there only have calculated Fi minus Ei whole square by Ei. So this 3.33 how I have calculated Fi minus Ei. So this will be 40 minus 30 whole square divided by 30. When you calculate that, you will get 3.33. So how I calculate this part? This will be your 35 minus 45 whole square divided by 45. When you calculate, you will get 2.22. Like similarly here, this will be 40 minus 50 whole square divided by 50. When you calculate, you will get 2. And here, Fi minus Ei, so this will be 85 minus 75 whole squared by 75. When you calculate, you will get 1.33. So now we have all the values now here. So we have to find the chi-square, which is summation we have to do. Summation means you have to add all this. So let us find the value of chi-square now. So in the next slide we have calculated. So you can see when we add, we will get the value as 8.88. Hello. Okay. Chi-square value is 8.88. So we will test this at 5% level of significance and 1%, both we will test. Okay, let us see. So what is the degree of freedom? We have to find the number of rows and columns first. How many rows we have? 1 and 2. How many columns we have? 2, 1 and 2. So 2 rows and 2 columns. So your degree of freedom become 2 minus 1 into 2 minus 1. So degree of freedom is 1. So your critical value at 5% and 1 degree of freedom is 3.841. This you can check in table. table is there with you. So now you can see here 8.88 value is greater than 3.841. It means we have to reject the hypothesis because the chi-square value is greater than chi-square critical value. So if you are rejecting the hypothesis means you are accepting the alternative hypothesis. So what's the conclusion? The two attributes are dependent. So based on the data or based on the survey, whatever the survey they have done, I don't know how they have done the survey, but based on the data, it concludes that skill of the fathers have significant effect on intelligence of the girl. So it says that if the father is skilled and if the father is intelligent, also implies that girl also will be intelligent. This is the test of independence we have checked based on the data. All right. So if anyone has any doubt, this is another problem. So similar format. So suppose that in a public opinion survey of answering to the question, someone has asked two questions. Do you drink? And second question, they are asking that, are you in favor of local option on sale of liquor? So data is given down there. So they want to conclude, can you infer that the opinion on the local option means the sale of the liquor, is dependent on whether or not individual drinks. So you have to check whether in the local area the sale of the liquor has any dependency that individual drinks or not drinks based on the data. So here the question A, yes or no. So 56 people said yes they drink and 31 said they don't drink, right? And question number B also 56, 31, 18 and 6, like that the data they have given. Now we have to check the hypothesis of dependency of two variable, sale of the liquor and whether they drinks or not. So the null hypothesis anyway is saying that two attributes are independent. It means the local option on sale of the liquor is independent of whether individual drinks or not. They both are not related to each other. This is your initial assumption. So to test the hypothesis, you calculate the expected frequencies. So already we know how to calculate the expected frequencies. If you want to calculate the expected frequency for 56, then your sum total, the row total divided by column total divided by the total number of sample. So when you calculate like this will be 87 into 74 by 111, you will get exactly 58. So like that I have calculated all the expected frequencies and their corresponding Fi minus Ei whole square by Ei. So this value will be again 56 minus 58 whole square by 58 as you have seen previously. And if you calculate, you will get 0.069. This will be 31 minus 29, which is Fi minus Ei whole square divided by Ei, which is 29. Calculate, you will get 0.138. Here also your Fi will be 18 minus Ei is 16. Square that and then divide by Ei, which is again 16. Calculate, you will get 0.25. Here also this will be 6 minus 8 whole square by 8. Calculate, you will get 0.5. So now we have to just add all this summation and we have got the value as 0.957. Now let us check this at 1% and 5%. So we have two rows and two columns, so degree of freedom is 1. So chi-square value at 5% and 1 degree of freedom value is already we have 3.841 that you can check from the table. And chi-square critical value at 1% level of significance is 6.635. Now you can see that 0.957 is less than even at 3.841 also, and this is also less than 6.635. So if the chi-square value is less than chi-square critical, we will accept the hypothesis H naught. So at 5% also and at 1% also, your H naught is accepted for both 5% and 1% level of significance. So if your H naught is accepted means yes, the sale of the liquor is independent whether individual drinks or not. They are not dependent to each other. The sale of the liquor is independent of whether individual drinks or not. So like that, if we have any set of independency we want to check in a real time, then test of independence is the important and good test of hypothesis. That is why we put that in a very important category. Okay, so I hope this session is clear now. If anyone has any doubt, you can just unmute yourself or you can put in chat box.